let's run the demo of the
data camouflage.
Yes. Data camouflage.
I'm Robert Carlson, and I'd like to thank you for joining us for our short demo on data camouflage. This exciting technology allows us to take data and apply a layer of obfuscation or data camouflage to disguise underlying patterns that bleed through using standard encryption methods. These patterns are important as they make breaking encryption faster and easier for the bad guys. For this example, we're using static images to illustrate the technology, but the same methods can be applied to audio, video, PDFs, and other documents and network traffic. We can mask the underlying data regardless of format. So let's open our first file, and we're just going to use the default password for this one. So here is Tux the Penguin, lovable Linux mascot and high contrast example. So this first box here is AES 256, and you can see the radioactive outline of Tux. Box to its right is a simple substitution cipher, and the box below that, permutation cipher. You'll note that all three of these have this lovely vertical striping, as well as the radioactive penguin. This is one of the weaknesses of non-polymorphic technologies. If your data looks pretty much the same before, it's going to look pretty much the same afterwards. However, if you look at our lower left-hand image here, here's our same penguin with just data camouflaging. There's no striping and no radioactive penguin. And if you look over here, we've applied that same image with AES. So camouflaged AES, we still have that beautiful random distribution, meaning that this technology pairs very well with other encryption and adding an extra layer of security. And then right next to that is the AES and camouflage data safely decrypted. Down here, this graph shows the percent change across the image throughout the process. As you can see, it's about 50% with some noise. This process is non-uniform for your security. Now let's go ahead and change the password here. And I want you to see how the data changes between sessions. Exact same image going in. And there's Tux again, sporting some slightly different and maybe a little less radioactive colors, but pretty much the same. In our data camouflage, completely different picture and completely different graph. We can have a different picture every time because our security is not limited by the data that we started with. Now, Tux here's a pretty small image. He's only about 22 kilobytes. Here's a slightly larger grain-scale black and white image from World War II. So it's about 1,000 times longer. As you saw, still pretty fast to run. The image here in the substitution and permutation box is a little fuzzier, but if we look in AES, you can still kind of make out the outline of the couple, and there's this nice line running through the road that you can follow. Down here in data camouflaged squares, lines aren't there, can't see the couple. All right, one last image for you. This is a full color image of the American flag. AES does a reasonable job hiding the flag here, but if you look, you can still see that flagpole right there. And then down here in our data camouflage squares, much better. So that's data camouflaging in a nutshell. We keep your data safe by taking the underlying patterns and making them disappear. Thank you very much for your time.
See, that's nice. That's a very visual demo.
Yeah.
That's really nice, right?
Yeah, the interesting thing there is if you take a look, you can see that patterns are bleeding through from the encryption, right?
Mm-hmm.
And those patterns still bleed through if you're using text files. And you can actually see that. We didn't bring text files in because it takes a little more refined eye to be able to see the patterns in the text file. But what we're actually doing is we're actually damaging the file and randomly flipping the bits. The graph at the bottom shows what percentage of bits has been changed. We try and keep that around 50%. And you can see it goes up and down, and over the longer and time that you look at that and the amount of data, you can see that it settles down at around 50%. The interesting thing is we don't have any control when we begin over what parts of that are flipped. So these bits can happen in runs, and they flip up to 16 or 17 bits in a row that flip, and then there'll be some that don't flip, and then some that do flip, and it's really kind of messy. And that's an example of how you can use a simple encryption to hide a pattern inside a pattern.